Good. Thanks very much. So there are many types of hazardous weather in the Arctic, and fog is actually one of them. And especially long-lasting fog episodes can cause quite severe complications towards, for example, marine traffic, but also to air traffic. And fog is a combination in models of different processes. So you can think of radiation contributing, microphysics contributing, but also turbulence contributing. And in this talk, I will present a new pathway that we're exploring to improve the prediction of such long-lasting fog events and also the occurrence, but also the disappearance of those fog events in an ensemble prediction system using the AROME-Arctic model. And this is part of work that we've been doing within the ALERTNESS project, which was a collaboration between the Meteorological Institute and the University of Bergen for this part of the work. And I can say that this was really exciting work at the interface between academia and operational service. And I really learned a lot with working together on the same tools. So I'm thankful for this opportunity, which was actually created through YOP. So this is an example of a long-lasting fog event that took place during YOP SOP 2 in the vicinity of Svalbard in July 2018, and we were here on a basically research vessel doing some small boat operations, and those were already hindered somewhat by the fog episode. This was actually related due to a heat wave from Central Europe that moved into the European Arctic and led to a lot of condensation and this long-lasting fog. So there's also an interesting connection here. But think of these events as really extreme events in terms of these low cloud ceilings that, for example, inhibit some air traffic to airports that don't have the necessary instrumentation to allow landings in all conditions. And so forecasting these events is really a challenge that operational centers do have. And I need to advance. And if you look at the 4 panels here on the, no, I don't have a pointer. If you look at the 4 panels here. You can point to that screen with this. Oh, wow. Maybe that's too much for me. Okay, so if you look to these 4 panels on the very left-hand side, this is the kind of the reference ensemble prediction system that is used in the MATCOP setup. And you see this very little variability between those 4 members that are shown here. Essentially, they all show a patch of fog and nothing less or more. And then in Frogner et al. 2022, there was this improvement with introducing what is called SPP, so stochastic perturbations of the parameters that the parameterizations are contain. And here you see a lot more patchiness, but also patches of fog now appearing in regions where there was not so actually no observations in the satellite imagery. So there was now this, sure, more spread, but maybe not necessarily in the right places. And this is partly connected to this picture that you see here on the very right. And this is kind of the perturbation field, which is perturbing the patterns with a random generator field. You inject a certain length scale and time scale to modify the parameters, but those are actually not based on anything that is meteorological. It's a purely stochastic process. So the idea of this presentation here is, can we find a connection between the model uncertainty that is inherent in using the parameterizations and kind of where we should perturb the ensemble such that those two are actually matching up and we're perturbing in the right place for the right reason. Many buttons to press here. So now one way of looking at this is to examine in more detail what contributions a parameterization scheme is making to the model field. And you see this on the very right-hand side. This is a vertical view of the contribution of the shallow convection scheme here to the specific humidity field, and in the orange color, so you see large contributions in the lowest levels. And then on the other hand, there is this compensating, and we just talked about compensating errors. So the schemes are compensating here, turbulence is compensating on the other side, and taking away, or kind of the one is handing over to the other, and they're transporting together and giving a small residual. And these kind of compensations of different processes, this handover of the material fluxes and the energy fluxes, are kind of pervasive throughout the model when we're looking at it with this tendency output. And for example, when you change to a different setup here, you see this dashed lines, for example, you still get these kind of mirroring contributions at different levels. And that goes also into the dynamics and the physics themselves, so they are kind of mirror images of each other. And that means when you have now a strong contribution from a certain physics parameterization scheme, for example, from shallow convection, and that has now an error because its computations are always a little bit in error as a generalization, then that error should scale with the contribution that it makes to the grid. So the stronger you have a scheme acting, the more it can be in error. If it, say, has always a 5% error, that error just gets bigger when it's more active. And now if we look at where the schemes are actually contributing, we can look at that also in the horizontal domain here. So this is from the AROME-Arctic actually for a colder outbreak case, because that was the case we started working with. You actually see in which locations the schemes are producing large contributions. And now the basic working hypothesis is here that this is also the foundation for looking at model uncertainty based on the parameterization. So where is the kind of the model error that is contributed from the parameterizations? And if we use that as a proxy for the model error from the parameterizations, we could use that to replace those random fields that I just presented in the previous slides. So I explore a little bit further in this colder outbreak case now, and I think I need to go to this slide actually. That's probably actually not the latest presentation that I'm now presenting, but the previous one. But we see these different patterns now emerging at different levels from where the parameterizations contribute. These are now examples for that same domain of AROME-Arctic. And you see here, this is the sum of the temperature tendencies from all physics parameterizations. So that includes, for example, turbulence and shallow convection and radiation and for that matter at least. And then at the surface you see here the strong bright area, that is where the sea ice edge is, so there is a strong heat flux contribution here. When we go a little bit higher up into kind of, say, boundary layer, this is a bunch of the lower levels looked at together. You see contributions from the turbulence mainly transporting the heat throughout the model vertically. And then if we go even a bit further up, just above the boundary layer, call it your middle troposphere, you start to see these contributions along these cloud streets where the shallow convection scheme is active. So you get these meaningful patterns that actually say here is a scheme active and contributing, but while it's contributing and doing its work, it's also always in error to some extent. And so we could use these fields, these patterns now, to inject those into the ensemble prediction system. Now in the second row here, you see also then the corresponding dynamic tendencies. So whatever the physics is doing needs to be compensated then by the dynamics to achieve basically balance and to remove, for example, energy built up or material built up. And so those terms are, again, really mirror images of one another. But that also means we can use the ratio between these two fields to see where we have a bigger contribution at any point in time from either the dynamics or the physics. And that's what the lowest row here is showing. Basically, these areas that are in red are showing where the physics processes are dominating over the dynamics. So these could also be used as a proxy for locations where we are more uncertain about or where we think the model error from the parameterizations is probably most prevalent. Now, let's see. So this is already almost everything I wanted to say, but I still have a bit of more time, so I will explore, show a bit how far we have come along the way of implementing this into the ensemble prediction system for AROME-Arctic. One first step is to kind of provide sort of a time filter, so we have a smoothly evolving field of these accumulated tendencies. We explore both the accumulated physical tendencies itself and the ratio between the physical and the dynamical tendencies. And now we can explore a bunch of kind of different dimensions here. And one of them is to look at how do we now transform this field, this perturbation, into a perturbation of a parameter. So we need to do some normalization and translate into a meaningful variation of the parameters that we have in different schemes. And in order to find that relation, we look, of course, at what has been done within the HARMONIE-AROME project so far. So there has been work on 11 parameters that are being perturbed in the SPP scheme. And we are now exploring basically using a single column version of the AROME forecast system to scan through the different parameters and look at are those responding in a linear way or in a nonlinear way to parameter changes. We thereby actually go very wildly into extreme values of that, I can point here again, of what is kind of recommended. We go like a factor of 3 over what is recommended just to see what is kind of the response of these parameters to extreme changes. So we can really get a feeling for, is it linear response, nonlinear response. And this is, of course, only possible with a very fast model, such as a single column AROME version, MUSC. And so that's also an outcome of this collaboration between operational and academic partners, is now this MUSC tool is basically something we use for the education, but also for research, and it's also used in operation. So that's a really great outcome. I can really recommend working with your National Weather Services anyways. So this is just an example of how we see these responses. This is a more linear versus a rather nonlinear response in the different parameters. And just to get to my conclusions here, I think the main innovation in this work is to find a clear link between what the uncertainties of the parameterizations is and how that can be exploited to actually perturb an ensemble prediction system so that we can get rid of these unphysical random perturbation patterns. I would be really interested to hear from you if you think that is a clear connection there, or if this kind of sounds like made up, if there's any gaps in the argumentation here, because I think it could be, if so, it could be a really clean way to perturb ensemble prediction systems in the future. Thank you.
Any questions in the room for Harald? Or online? Okay, I have a quick question. So you started talking at the end about a sort of perturbed parameter approach that you were going to experiment with. Have you done anything specifically for fog in that space yet?
Yes, so the single column experiments are actually for, oh yes. The single column experiments are for a fog case. So we are looking into fog in the vicinity of Bjørnøya during SOP2.
And any results?
Now we're just looking at how sensitive it is, and then we will actually take it, of course, to the full three-dimensional model version in the next step. Yes, work in progress.
Time for one more question, if anyone has anything in the room or online.
So this whole notion of compensating errors, you know, you showed your nice plots and they're mirror images, and I think that I don't actually do a lot of model analyses, but some on my team do, and we see a lot of plots like that, right? I mean, energy or matter is conserved in some way. So if you get something wrong, you have to get something else wrong in order for things to kind of loosely be balanced. So how do we actually figure out the cause of that, right? What's forcing those issues versus responding, right? So some of those parameters are simply responding to some other imbalance that's going haywire. So how do you diagnose that?
Yeah, I think that's a big part of how we can use these kind of informations is, can we connect them to something that we can observe? So if it's kind of, if we're pulling apart one physical process into two terms, then they will show up as, very different terms, but in the end effect they will be a physical quantity. maybe we can find parameterizations that are, if we pull them apart, also observable terms. So that would be kind of a way to constrain schemes. I don't know if that's possible in every cases, but it may be in some cases, like radiation, for example.
Okay, thanks a lot, Harald.